You can see it. So no, thank you
Yeah.
so much for the invitation to talk today. And this is a new talk, so it's very exciting to put together a new talk and to kind of synthesize some of the work that Craig and I have been doing over a number of years with a number of people who I'll highlight during the course of the talk appropriately, hopefully. And it's really a love letter to Craig, I guess, because I'd never really worked with igneous geology in any real sense before I met Craig about 9 or so years ago. But I was always intrigued by these things we were seeing in seismic reflection data. And Craig brought with him that structural geology and igneous geology expertise that then allowed us to do some of the work that I'm going to present to you in the next 40 minutes or so. So let's get off with some definitions. What are we talking about when we talk about igneous sills, ground deformation, and 3D seismic reflection data? So as you'll see on the right-hand side of this, right-hand side of this slide in here is a laccolith body in place into these layered sedimentary cover rocks here at the basement cover interface. And this is from the Henry Mountains area in Utah. And you can see the scale in here. Laccolith, which is a couple of kilometers thick and about 5 kilometers basal diameter in this cross section. You can see that the emplacement of that laccolith, that sill-like body, which has got, which is inflated, has deformed the overlying country rocks, forming this thing we call a forced fold or the ground deformation. Underneath here, you're seeing a CT scan model of Sam Popper from, and you can see the scale in here. It's a very small model, but what you're seeing here is a magma analog in here, which is effectively golden syrup being pumped into a sand and clay mixture, which is the host rock in this instance. And you can see as that magma or that syrup comes in, you're inflating a sill and you're getting ground deformation of a similar kind of style to what you're seeing in this cross section from this geological outcrop in here. And you can see the ground uplifting above that inflating laccolith saucer-shaped sill, I'd say. Also important to note here are two other styles of deformation which are associated with the ground deformation. One is the formation of these circumferential almost ring faults, these reverse faults, which are coming off the upper tips of these inclined sheets at the edge of the sill-like body, but also a series of mode 1 dilational opening fractures across the top of the fold, which are accommodating the line length increase as the ground deforms. So there's folding and faulting taking place to accommodate this emplacement of magma. And what we're going to be using today are these data, okay, in the bottom right. This is seismic reflection data, and this is an image from the Canterbury Basin. We're going to look at this a couple of times during the talk. And what you can see here, nice image in seismic data, is an igneous sill emplaced in, you can see these sub-horizontal reflections in here, are a layered host rock. These are sedimentary rocks, and you can see above the sill in those host rocks, you can see a fold of a similar geometry and scale to what we're seeing in the field in here. So that's what we're going to be looking at today, ground deformation above inflating igneous sills using 3D seismic data. Why do we care about this? Well, I'm talking to, preaching to the converted here. We have an interest in geohazard analysis and related mitigation. So we can use geodesy and looking at volcanoes from space, as Tamara said, to try and work out how a deforming volcano may tell us something about the size and volume and shape of the forcing member, the intruded body. But remember, we've got a range of different geometry types we could select from when we're trying to invert a geodetic signal or seismicity data. So we could have a saucer-shaped sill like this, an inclined sheet, a dike, or a more tabular flat sill like this. So, and all of these are kind of giving us, in many ways, non-unique ground deformation signals. So we're trying to invert that shape. We also care about ground deformation because it's important for resource extraction and geoengineering. As you can see in this image in here on the right-hand side, this is a seismic reflection profile. There's an igneous sill I'm tracing out here at the bottom. Above it, at the base of the Paleogene, there's a green reflection that has been mapped, and that's actually the reservoir layer here. It's a deep water sandstone. You can see where the well has been drilled, this red line coming down, and this was a gas discovery called Tulipan offshore mid-Norway. So we can find petroleum resources in the related ground deformation. From a geohazards perspective, or geoengineering perspective, sorry, we may also view these sorts of traps as being potential sites for carbon dioxide storage as well, if we have the appropriate rock properties in the subsurface. So I've shown seismic reflection data twice to you already, and I've not really explained to some of the community here what those data are. So I'm going to give you the complete idiot's guide to reflection seismology in one slide, or why rocks and wiggles are related. So here's a marine seismic acquisition. We have a boat sailing on the sea. We have a source of acoustic energy behind the boat, and it's an air gun. In this case, it releases a big bubble that pops, and the related acoustic waves travel down along these black lines into the Earth's subsurface, reflect back off these different layers, and are recorded back at these things trailing behind the boat called hydrophones. And that repeats a number of times on a number of different sailing lines of that boat. Critical here is the reflection coefficient, and that's the ratio between the downgoing energy and the amount of energy that's returned back to the hydrophones. The reflection coefficient, that ratio, is controlled by something called the acoustic impedance contrast at the layer boundary. So you can see there's different layers of rock in here, and some layers have different properties because they've got oil or gas in or water. And that reflection coefficient and the acoustic impedance contrast is controlled by the density and velocity variations. Now, this is really important for us as igneous geologists if we want to look at magmatism. It's because the igneous rocks typically have, as you see here in this table, much faster P wave or acoustic wave speeds than sedimentary rocks up in here. They normally have these wave speeds of above 5.5 kilometers per second compared to typically 2 to 3 to 4 kilometers per second for these sedimentary rocks. So if we encase these crystallized igneous rocks inside these acoustically slower sedimentary rocks, we should have really good reflectivity from them. So we should be able to image them quite well. And in fact, that's what we see if we go to the Bight Basin offshore southern Australia in here. So just for context, I'm going to talk you through this quite carefully. Here's the seabed you can see labeled in here. The grey colour here is water. You can see these subhorizontal layers in here. These are layered sedimentary rocks. In this instance here, they are non-marine and clastic rocks of something called the Hammerhead Delta. And here we have marine carbonate rocks in here. Hopefully your eye is immediately drawn to these high amplitude bodies which are encased within this lower amplitude subhorizontal reflectivity. These are these igneous sills. And sitting on this blue horizon here are some triangular bodies I'm not going to talk about today, but these are volcanoes. You can see a really big volcano in here imaged in this seismic reflection data. The blue horizon here is Eprisian. This is Middle Eocene. So you can see we're imaging the volcanoes plus their underlying plumbing systems, these sills. Now, if I start to scroll along, you saw the scale bar there, that's 10 kilometers. You're looking at a really long seismic line here. These 2D lines we're going to be looking at today, these 3D volumes, cover hundreds to, well, thousands of kilometers squared, and they can image down to depths into the lower crust. So we can actually look at these sill complexes down into the lower crust. On the right-hand side of this profile now, you can see a sill here and a laccolith at shallower depths in here. And you can see really beautifully imaged is the ground deformation above both of those bodies, these forced folds. We can work out the age of these folds and the emplacement of the sills by the fact that these Eocene, these upper or late Eocene rocks here are onlapping, they're thinning across these folds. So we have an explicit stratigraphic record of the kinematics and the timing of the folding and also the emplacement of the underlying igneous bodies. So what we're going to do today is we're going to go through, I'm going to start off with some, like a bit of a retrospective of where we've come from with this work, not just Craig and I and co-workers, but other people. And then I'm going to ratchet it up. I'm going to get to some very, very complicated things that we've realized more latterly in our research and put out a bit of a plea to the COMET community to tell us your thoughts about some of the work we're doing as we progress it. So let's start off with some of the original work. Almost 20 years ago, this was work by James Trude at Cardiff. And here's one of these seismic reflection profiles, okay? What you can see, sorry, my cat is trying to escape from our front window and hopefully she won't. What you can see in here is a number of igneous sills. One of them is labeled here in P. So you can see these igneous sills encased. And these are encased in Paleogene deep water mud rocks. And these are from the Faroe-Shetland Basin. There's a very subtle forced fold above this sill. You can see the green horizon is buckled up and then down again. And that's because of the emplacement of this sill. So there was a recognition that there was a spatial correspondence between sills, this uplift, and also in this instance, they had well data to work out the age of this pink package in here. And this pink package was late Paleocene. So they were able to constrain the timing of emplacement as well as that spatial correspondence. But there was no analysis at this point of the thickness of this sill and the magnitude of the ground deformation. It was purely about just a general kinematic model, no real thinking about mechanics, and there was some interest in the timing of sill emplacement. A few years later, Dr. Hansen, as part of her PhD at Cardiff, looked again at the Paleogene sills in the Ferro-Shetland Basin. You can see a really well-imaged Paleogene sill down in here, again emplaced into these Paleocene mud rocks. A really big fold. Just give me 1 second. The cat is escaping. Sorry. Sorry about that. You can see there's a very big fold developed above this sill in here. And this was one of the first times then when there was started to quantify the relationship between sill thickness and the fold amplitude, if you will. So what they did is they measured the sill thickness across its diameter, this saucer-shaped sill, and the amplitude of this fold above a datum. So you can draw a datum line. And this is what they found. This was a 3.5 or 4 kilometer diameter sill. And the sill thickness is shown with the grey squares, and you can see that the sill thickness was up to about 300 meters. What you could also see is the fold amplitude, which is the black diamonds, and you can see the fold amplitude was roughly the same as the sill thickness. So you can see that there were, again, they kind of were much more quantitative about that relationship. They explained this because there was this close correspondence between the amount of ground deformation and the sill thickness, that it was a pure elastic bending, that all of the sill thickening and the sill inflation was taken up in pure elastic bending of the overburden. And that was the main mechanism at play. There was a recognition that seismic data were limited in that you can see there's a mismatch in terms of how wide the sill is versus how wide the fold is. The fold looks wider than the sill, but that might simply be because we don't have seismic imaging right at the tips of the sill. As we tune this, as we thin the sill out geologically, geophysically, we can't see it. So that might explain the mismatch. So it was a very, for me at least, it was a very insightful paper. Craig and I went away with Freddie Briggs, who's down in here, and as part of his MSci project, we picked up on these as we went into in 2013, early 2010 times. And again, looked at these sills here. These sills were from the Exmouth Plateau. These were in place within Jurassic mud rocks. You can see a force fold above the crest of the sill. And what we could do now is we could go away and make actual maps of this because we had 12.5 meter line spacing in these seismic volumes. If you look at a map of that horizon D, you can see here, sorry about the color bars. It's a completely inaccessible color bar, probably for some people on the course, so I'll talk you through this. This area I'm circling here is red, and this is sticking out the screen towards you. And this is lower around here. So you're looking at a pimple pointing out. So this is a dome above this sill. The outline of the sill is shown by the black dashed line, and it's lying underneath this surface as you're seeing it. So again, you can see that spatial correspondence between the sill and the fold. You can also see these grey blobs in here, and you can see on the seismic profile here, there's a grey mound. This is a magmatic vent, and this magmatic vent is attached to the sill tips. It's fed probably by hydrothermal material and maybe some magmatic material sourced from the sill itself. And because it's sitting on a horizon of known age, we can use that magmatic vent distribution to constrain the age of both the folding and the sill emplacement as well. In this case, these are Kimmeridgians, they're latest Jurassic sills. We went away and did a similar thing as Hansen and Cartwright. Again, you're going to see a few of these graphs in this talk. This is distance along the x-axis across the sill fold pair. This is thickness or amplitude on the y-axis. And you can see here, if you look at the blue and red lines in here, this is showing you that the sill thickness is up to about 200 to 300 meters, but it's substantially greater than these circles in here, which are the fold amplitudes, the corresponding fold amplitudes. So in this case, it doesn't look like all of the sill thickness was being translated into uplift at the free surface. And I'll come back to that later in the talk as to what mechanisms in the next slide, as to what mechanisms we thought was accommodating that. The other thing to show you on this slide is this idea that faulting is also important. As you can see in the map in here, there are a number of faults in here which seem to be located just above the crest of the force fold. You can see them in cross section here. And so we think, again, they're very similar to these are shear fractures as opposed to pure opening mode fractures that we saw in Sam's models on the title slide. So based on this mismatch, we said, well, okay, maybe elastic bending isn't the only thing at play. You know, we have these sills which have a diameter to depth ratio greater than 4, right? So they're quite broad sills in place at relatively shallow depths, therefore they should be able to hydraulically uplift their overburden, and that might apply. But because we're seeing this mismatch, maybe we have a model whereby the sill is in place, but actually what we have is considerable host rock deformation. So we expel pore fluids, we have pore collapse, we have a porosity decrease overall, not just in a contact metamorphic zone, but maybe over a slightly broader area, meaning that as the sill starts to inflate and widen, as you see here, we do get some uplift of the free surface, but not the same amount of uplift as you'd imagine for the amount of magma that was being in place at the same time. And then we develop these things we call inclined limbs, which then feed these vents at the paleo seabed in that case. So it started to make us think about the relative contributions of elastic and plastic or inelastic non-recoverable strains, non-recoverable deformation within the host rock during sill emplacement. And, you know, we went back to the Bight Basin actually, because we'd already been doing some work there and looked again harder at these and we looked at this in that big seismic profile which animated earlier on. Here's a deeply emplaced, relatively thin sill. Here's a relative, remember the blue horizon is that middle Eocene horizon. That was the paleo seabed at the time of sill emplacement. And here we have that laccolith at shallower depth. So this was emplaced, you know, maybe 200-300 meters beneath the seabed. This one was at about 500 meters below the seabed and it's thinner. And accordingly, there is less uplift above this sill than there is above this laccolith. And again, drawing your eye just here to the normal faults, which are clustered around the apex of the folds, which are these brittle deformation that accommodates brittle deformation of the folds in there. What was important here is I remarked earlier on that these are non-marine host rocks. So these are actually something called a hammerhead delta, and these have got large, thick and extensive coal layers. So one reason we think that here there are these strange thickness fold relationships I'll show you in a moment is because we actually have this coal-bearing host rock. So we went away and looked in a lot of detail at about 30 or 40 sills in this Bight Basin data set and looked at, on the x-axis here, the intrusion thickness versus the y-axis here, which is fold amplitude, with the one-to-one line being highlighted here in red. And you can see that for all of these fold sill pairs plotted up in here, that typically we have anything between, you know, a one-to-one relationship down to only a quarter of the ground deformation, or the uplift, or the uplift, sorry, is only a quarter of the sill thickness, even for relatively shallowly in place sills with large diameter to depth ratio. So these are sills which should really produce quite a lot of ground deformation, but they're not. And one reason we think that is because of, like I said earlier on, they're being emplaced into a host rock which is able to deform in other ways. We can have fluidization, we can have porosity collapse as well. And just going back to this porosity loss idea, and I think Tara Stevens is on the call, and I know she worked out in Utah for part of her PhD. But you know, looking here at this this igneous sill, which is emplaced into this high porosity sandstone in here, you can see the blunt nose of this igneous sill just behind the person for scale. And you see the force fold within the sandstone. If you go along that sandstone layer, and the sandstone is Jurassic, the sill is Tertiary, so we know that this layer in here regionally is relatively isopachous, it's similar thickness, but you can see above the sill it's thinning. And so that means that this layer has actually has been strained by this inflating laccolith that you can see underneath. The porosity measurements taken along that bed are shown here above, with porosities going from 0 to 45% porosity. And you can see a general decrease in the porosity within that sandstone. And that's probably because there has been porosity loss induced by the inflating sill. And this was all going on under a couple of kilometers burial depth. Okay, so you've actually had vertical flattening of the layers as the sill is inflated. And therefore, one way of accommodating that is with this sort of inelastic mechanism. And there has been work done looking at the contribution of faulting and fracturing, as well as just kind of more diffuse porosity loss as well. But this is one mechanism by which we can accommodate ground deformation above igneous sills. And these are obviously cryptic to our seismic method. We can't see this. What we're seeing is the mismatch in terms of the kind of macro scale strain, if you will. Let's now look at force folding and what it can do for us in terms of informing us about regional magmatism, and also about how prolonged ground deformation can be. Because in many of these cases I've showed you so far, these are kind of like fairly discrete pulses of magma injection. And like I said during this talk, I'm going to sort of ratchet up the complexity, if you will. So for this, I'm going to take us here to a place called the Northern Rockall Basin here. So this is offshore and Northwest Ireland, part of the British-Irish Paleogene Igneous Province, associated with breakup of the North Atlantic. In this location in the Irish Rockall Basin, when we started this work originally, it was one of the first projects Craig and I worked on together. We had a number of principally radiometric age dates for a number of basins going northeastwards along the margin all the way towards the Vering Basin. And they were quite scattered. And, whether these are discrete pulses or whether these are radiometric date uncertainties or whether this is protracted magmatism was still a bit of an open question, and certainly something that was poorly constrained for the Irish Rockall Basin in particular. So we used a 3D seismic reflection data. This is bathymetric data, and here this is the shelf to the slope. We had a 3D seismic data set just to the south of something called the Hebridean Terrace Igneous Complex, and two wells. I'm going to show you some of the well data in a moment. If we take a seismic line between those wells, as you see here with the green line, this is what you see. For scale, this is 5 kilometers horizontally. This is a time migrated seismic volume. So this is 3 seconds, but at these velocities, this is about 5 kilometers in the horizontal axis you're seeing. Hopefully your eye is drawn straight away to this cluster of igneous sills, which we've highlighted in red down in here. And these are emplaced into Cretaceous to basically earliest Paleogene marine mud rocks again. So there's this big cluster of sills, 82 sills seismically imaged, or we were able to map in here. The other thing, in addition to the sills you can see, is there's a very broad dome above the top of the sills. You can see it in the geoseismic drawing, but let me take you back to the seismic data itself. You can see there's a broad dome there at broadly Paleocene level. And you can see that's what actually was targeted by this well. This is called the Errigall well. Mount Errigall is a mountain in Ireland. So they drilled this well down into the top of this dome to look for hydrocarbons. But for us, that was really cool, right? Because then we knew the ages of all the reflections, the Cretaceous in K, Paleocene P, and Eocene in E. And yeah, so this is what they were targeting, some Paleocene deep water sands, but that's not really too relevant for this particular talk. But this is the constraints on the stratigraphic ages we had. So let's now look at the force fold structure. So this is the force fold structure at the Paleocene level. So let me just go back. I'm going to show you, this is a map at this level in here, highlighted on this simplified stratigraphic column. And north is to the right here. Again, the color scheme is not great, but let me just highlight for you here. The area I'm highlighting here again is one of these pimples. This is a dome that's sticking out the screen towards you. And you can see the well was drilled right on the apex of that dome. So this is this big diffuse force fold, and you can see it's kind of like 30, 40 kilometers in diameter. It's a really large structure, substantially larger than those folds we looked at earlier, which were above very discrete sills. And there's the seismic profile. So the Paleocene level is there. So you can see there's the dome, there's the well, and here's all these sills which are clustered underneath that dome. So you can see again that broad spatial correspondence between the sills and the folds. You can see all the sills that were mapped in here. Craig was a complete hero. I don't know if he mapped all 82, he can tell you in the Q&A, but he certainly mapped a lot of the sills. I think he did, because I'm going to show you some of the sills in a moment. You see the well TD just above. So here are some of the sills that were mapped more than 2 kilometers beneath the Paleocene horizon. So these are the deep sills. So this is the deep lying sills. And you can see here, they're just tessellated, right? So we're just showing them all together, but you can see they're very densely clustered here in the north and less densely clustered towards the south. This is now the sills between 1 and 2 kilometers beneath the Paleocene horizon. So these are the intermediate level sills. And again, you can see them all in the map at the bottom, but they're a bit more diffuse. And if we go and look at all the sills which were in place less than 1 kilometer beneath the Paleocene seabed, you can see here they're clustered in the north. Now, if we add all of those up, the deep, intermediate and shallow sills, and look at their, if you will, the density, the vertical stacking of those sills, this is what you get. So areas of the warm colors, the oranges and the yellows, are where you've got 4 to 5 to 6 sills stacked vertically. And the purple areas here are where we've only got 1 seismical image sill. And clearly what you can see is a very good correspondence, between the sills, where we've got more densely stacked sills, and the apex of the ground deformation, the apex of the force fold. So it looks like, again, there's this very good correspondence, but here it's not just one sill that's driven the ground deformation. Clearly there's multiple sills that have been injected. In terms of the timing, we can go and look at the thickness patterns above the top of the sill. This is now just the Paleocene horizon being shown, which we showed before at this level, and that's the Paleocene horizon here. If you look in detail, you'll notice that show the first map. This is the Paleocene isopack, so the thickness of the Paleocene rocks around this fold. Yellow is thin, this area over here is purple and it's thick. You can see maybe there's a bit of thinning across the fold, but it's not too pronounced. But if we look at the Eocene isopack, so this is now the thickness of the rocks between P and E here, there's clearly thinning of that package onto the fold, indicating that the fold was massively growing or underwent a major period of growth during the Eocene. But there is some thinning and on-lap relationships in the Paleocene as well. And that led us to this model, whereby we have pulses of injection of magma leading to quite complex and protracted ground deformation. So we have initial flux of magma. We get folds growing above these initial injections, these initial intrusions. We then start to coalesce the folds. So they start to grow in amplitude, but also diameter. They start to coalesce to create these almost megafolds like you see in here. And these could be new magma batches which are coming in and under-accreting or over-accreting already crystallized sills, or they could be mixing with a mush. Or, you know, we don't really know that because we don't have the well data. We don't know if these are laid intrusions and so on. But suffice to say that this is we think the most appropriate kinematic model is that this is telling you about multiple phases of injection. Now, where that leaves us in terms of the regional magmatism, to go back, what this suggests is that the Irish Rockall Basin underwent a really protracted phase of magmatism, and that's recorded in the ground deformation and the related stratigraphic patterns as you see in here. So about 15 million years or so of progressive growth of these folds due to progressive inputs of magma. And what that makes us think is that these dates are probably okay. There probably are several pulses of magmatism in the different basins along the northeast Atlantic margin. And it's just that in the Rockall Basin, where we've studied the force fold, the related ground deformation, we're actually being able to constrain that more directly. So let's ratchet it up a bit more and go a long way away from the offshore island. Let me check the time, okay, to the Canterbury Basin. And this is work done by Jennifer Reeves, who was an MSci student with Craig and I a few years ago. So she went down to the Canterbury Basin, used the 3D data set, 2D data set, as you're seeing, down in here. I'm going to show you this. This is like a stratigraphic column. Don't take away the thing I really want to draw your attention to here is that this is an area with a very complex magmatic history, okay? In many of the places we've been working up to this point, we thought they had relatively simple magmatic histories. Here, from onshore studies and some offshore data, we could see that there was A, B, C, and D. There were several pulses of temporally discrete magmatism recorded by things other than seismic reflection data. Okay, and we could see here that this magmatism was relatively protracted over 30 odd million years or so. And there was some, you know, there was this deep marine mudstone host rock. So Jen went away and was going to look at the growth of the force folds here. And it's an absolutely beautiful data set. If anybody wants it, we're happy to share it. Basement rocks down in here, layered sedimentary host rocks in here. We have borehole data which constrain some ages through in here you're seeing in red on the right. And these are these wonderful sills in here. So these are big sills, 4-kilometer basal diameters or so. You can see the inclined limbs at the edges of these sills are up to 500 meters tall. You'll also see that some of these sills are associated with reverse faults at their tips. You can see there's reverse faults, and they'll be important in a moment. These big folds above the tops of them extend to a considerable thickness of the sedimentary host rock across layers of variable ages. And also, if you look in detail here, this is horizon 5, this is a late Eocene horizon. The folds are quite unusual, right? They're not the simple domes we looked at earlier on. This fold at deep depths is relatively flat topped. This is down in the Eocene level, but then we actually have this like dome, more rounded top at Miocene level, which is not what we saw before. We saw a fairly consistent geometry vertically, albeit that the folds actually decreased in amplitudes upwards. So there was something quite horrible about the folds in this data set. So I'm going to show you now a map of that H5 horizon to show you the geometry of the force folds. Again, the color bar is not great, but I'll just highlight a few things for you. The white lines here are the sills lying underneath this surface. And this area here is a relative high, another relative high, and another relative high. These are force folds sitting above the white outlined igneous sills. Fold 3 looks kind of normal, right? It looks like a dome like we saw on the earlier examples. But this fold 1 is kind of weird. You can see it's actually got a depression above the top of it. You can see it's got like an uplift here around the edge of the sill, an uplift here around the edge of the sill here on its northern side, but we actually have a depression in the middle. So it's not just an uplift, there's actually a kind of collapse or a depression across the apex of that fold. So let's look at that in a bit more detail. What do we see geometrically and in terms of the stratigraphy? So here we're looking at a slightly shallower stratigraphic level here. This is kind of the Oligocene to Miocene level, and this is the seismic data on the left-hand side. And straight away you can see that there's this depression across the top of this dome, and you can see it here as well. And if we look at the stratigraphy, here we don't have these simple thinning and onlap relationships. We have packages of rock which are restricted to the fold crest, these grey packages, the dark grey packages, sorry. We have light grey packages here, which are more tabular and extend all the way across the fold. And then we have other packages which look like they're either onlapping or truncated across the fold. So we have this really weird stratigraphic record where it looks like there were periods when the fold was being uplifted, there were times when the period was in stasis, and there were periods when the fold was actually collapsing as well. And we see this in the thickness maps as well. If we look at the thickness map for the package I'm showing here, this is it here, blue is thick, the red color is thin. You can see it's actually, there's a thickening into the collapse structure on top of this force fold, and that's sort of what you're seeing here. It's mainly taken up in this unit here. But if we go to shallower levels, go up into the Pliocene, from the early Miocene into the Pliocene, we can see fold 3 is highlighted, fold 1 again, and you can see that there's a slight thinning of stratigraphy. So that looks more normal compared to what we saw earlier on. So what do we think was going on here in this Canterbury example? Sorry, just to show you that there are there's some vents here as well, which allow us to constrain the magmatism ages, just like we saw earlier on. So we had this model earlier on where we said, okay, maybe there is this trade-off between elastic and plastic deformation, and it might be related to porosity loss and dewatering and fluidization. But there may be a range of other particular models that may be appropriate in here. So one might be a time where we have sill, emplacement, and ground deformation. There's then a pause in magmatism, and then we have more magmatism and inflation or further inflation of that sill. So that would allow us to build up these quite complex stratigraphic patterns in the overburden. And that's very similar in a way to the model we had for the Rockall Basin. We may have a model here instead where, in fact, we have emplacement of a sill which starts to inflate and starts to develop inclined limbs, but then those inclined limbs, as you can see here, are only going to grow because they're taking magma from within the sill itself. So we inflate the sill, the inclined limbs start to grow, magma then migrates along inside the sill, starts to pump up the inclined limbs, but actually evacuates magma from inside the originally inflated body, meaning that we have this collapse structure above. And then we can have a secondary period of injection of magma, which then uplifts this complex record in its roof. And finally, we could have in here a time where we have a magmatism, we have ground deformation, it all looks good, and then we have a secondary pulse of magmatism, represented by very thin subseismic sills in the overburden. And this might actually explain, in this case, why we have this change in the geometry from a flat-topped fold at deeper depths to a more rounded crested fold at shallower depths in here. So that might be appealing in that sense. So just going back to the Canterbury Basin, again, this is now going a bit further northwards, just the last couple of examples for the talk. And going back, and now what we're going to do here is, this was one of the biggest realizations I think we had, right? A lot of these are ancient examples, clearly, right? I've been talking about Eocene intrusions, Cretaceous, Paleocene intrusions. These are all buried now under very thick sedimentary sequences, as you can see in here. And this data set was really awesome we worked on here, because we had a well resolution one, which drilled all the way through the host rock and the fold. You can see there's a sill down in here, there's a fold above it, but it also drilled into the sill itself. It drilled 50 meters into this thing called the resolution sill. And so we had age constraints on the horizons, but we also had direct calibration of velocity information for both the overburden and the sill itself. And you can see that this is actually, the y-axis here is in depth, so we were able to depth convert the time migrated volume. Not going to talk through all the well data in detail, but here are the well data: spontaneous potential, caliper, gamma ray, and sonic velocity. You can see shaded in red at the bottom is the resolution sill has penetrated, and this is the two-way time data, which allowed us to do the depth conversion. What's important down in here, there was a contact metamorphic zone down at the bottom here that was described in the well data. You see it in the petrophysical logs as well. That was about 25 meters thick, so just above the top of the sill in here. So this was a really exciting chance to then go back to the seismic and say, well, okay, if this is all buried, how might the shape of this fold have changed through time after it was buried? Because remember, the crystallized sill is largely incompressible, but the sedimentary rocks are very compressible. So we can actually modify the geometry of the fold and the amplitude of the fold, and could that explain the mismatch between the fold amplitude and the sill thickness? So we could do this, right? We could go back, measure the sill thickness, look at the amplitude of the fold, but then actually do what we would call decompaction analysis, so backstripping and decompaction. So we're going to remove these overburden layers and try and recover the sin emplacement geometry of folds. So this was work underdone by Murray Hoggett at the University of Birmingham towards the latter part of his PhD. This graph is complicated, but I'll talk you through it. So this is the x-axis. You've seen this before. This is distance across the sill fold pair. You've seen this as well on the y-axis here. This is sill thickness or fold amplitude. Pre-decompaction, when you look at the seismic data, this is what you see. The red line here is the sill thickness, okay, the red solid line. And we had a sill thickness of around, a maximum sill thickness of 138 meters with a range between 117 and 187. That's because of our understanding of what the sill velocity is, okay? So we're calculating that based on seismically mapped sills and our knowledge of the velocity. The fold amplitude is shown by the gray dashed line in here, okay? And you can see the gray dashed line in there. And the fold amplitude was around about 127 meters. And that gave this fold to fold amplitude sill thickness ratio of about 0.92. So, kind of broadly similar if we were using quite conservative velocities for the sill thickness. What then you're able to do is then obviously decompact this dashed grey line. You don't need to decompact the red line, remember, because that's the crystallized sill, but you can decompact the grey line by removing those overburden layers and seeing what that line would have been like at the time of emplacement. And that's what that grey shaded area is. A maximum, there, and a minimum for our knowledge of the host rock compaction parameters. Again, your sill thickness stays the same as it was in the pre-decompaction state. Your fold amplitude, though, grows, and it grows by anything from as small as 4 meters up to about 60 meters or so, because you're fluffing out, if you will, the overburden, the host rock. And that actually means that you kind of reduce this, you know, the mismatch between the sill thickness and the fold amplitude, which leaves you with this, you know, they may be more similar than previously thought. The slight mismatch in this case might be because this sill had a relatively small depth diameter ratio, because it was quite deeply buried and it was quite narrow. And, you know, again, this has kind of informed some of our future work where we're trying to think about these different deformation mechanisms that are occurring as sills are in place. I think let me just check the time. Oops. Okay. Yeah, and I'll move on to this last example in these last two examples. Sorry, tomorrow I'm just going to go back to. Hopefully, you can still see that. Can you see that?
Yep, we got that.
Yeah, cool. Yeah, last two examples to finish us off. Really gnarly ones. You know, I said I'd kind of ratchet up the tension, if you will, during this talk. We went to this basin here, the plateau again, and you can see these really kind of nasty looking igneous bodies in here, which look like they're super thick, almost, you know, 900 meter thick sills in here with these really broad, high amplitude domes above the top of them. I'll just show the interpretation in there with a number of intra fold faults. You can see the 3D image of horizon C is shown. Sorry, it's shown on the right hand side in here. So these coalesced force faults. Fold amplitude, almost 300 meters, less than the sill thickness. We've got these different types of folds. And what's very bizarre here is you've got this very strange stratigraphic record, all right? What you've got is you've got a fold at horizon C across this fold one. Let's just focus on fold one. We can see that this package is kind of onlapping onto that fold, but thickening across this peripheral fault, this circumferential fault. And then package D to E is thinning and onlapping. You can see it's much thicker here, much thinner across the fold crest, higher up. So it looks like you had an earlier phase of fault-related deformation associated with emplacement of this sill, and then a later phase of inflation of the fold, which is then recorded by thinning of the package between D and E. So this was a stratigraphic record, and I remember doing this work with Jonathan Hardman. He was the poor sci student at the time, and it was a real headache. And this was the best model we came up with for this particular example. Here we have the pre-kinematic setup. We emplace a sill in here, or a sill complex, which is predominantly almost piston driven. There's a minor amount of folding, but there is basically brittle deformation. We have a piston-like uplift of the overburden. We then have that recorded by that package C to D, which is thickening across the fault, but doesn't actually make it across the crest of the fold. We then have a subsequent phase of sill emplacement, which then forms this broad arch and is recorded by thinning of stratigraphy across the top. So two phases of temporally and kinematically quite distinct deformation above these sills. Now, the reason we quite like this is if you go back to the seismic example, how gnarly these sills looked, this could simply be a number of clustered sills with slivers of host rock between them. So it's not really 877 meters thick, as we've shown here with the yellow lines. It could be much thinner in terms of the actual igneous material, okay, which would also explain this apparently huge discrepancy between the fold amplitude and the sill thickness. And yeah, we just need to be careful when we're using growth strata. So last final example in here, okay, is just again staying with the Exmouth Plateau. This is a time structure map down in the top Triassic. This is a big map. This is 25 kilometers for scale in here, and this is a much more appropriate color bar, hopefully. And we can see rift-related normal fault network in here, and then associated with that in gray, we're just highlighting here a number of sills, which I'm going to show you in a moment. But there's a number of sills which are emplaced into basically a non-marine host rock about a kilometer beneath the paleo seabed. This is what we see here. Now, this is just to show you the contribution of faulting to ground deformation. at the same time as folding, like we saw in the previous example. This seismic line here goes across a location approximately in here. Here's the sill. It's really nice. You can see the top of the sill. It's so thick you actually get discrete reflection off its base. You can see there's a forced fold above the top of the sill, but you notice that the inclined limb on the eastern side of this sill is actually injected up the fault, up the normal fault plane. So it's actually, been injected up into that permeability provided by the deformation zone in the fault. So you can see there's we have well data. We can build like a seismic stratigraphic model, which allows us to constrain the ages. But this is just to show you, the spatial relationship between the fault, the sill, and the overburden. If we look at the sill thickness in map view in here, the dark color is thick, the light color is thin. We can see the sill is very thick in this location. We've done a lot of work around sill propagation, but that's not for today. And you can see that the eastern margin of the sill is bound by that normal fault. This is the suprasill structure. So this is the force fold above the sill. It's actually quite a complex dome. It's not a simple dome. The dashed line is showing the outline of the underlying sill. There's like a number of different closures above this sill. So it's a bit like some of the Canterbury examples. And then this is the fold-related growth strata. So this color's thin. This color here is thick. So you can see thinning of stratigraphy up onto those domes above the sill. If you go and look at the fault-sill relationships in here, the sill thickness along distance is shown here in the red line. So this is coming along the fault. So you can see the sill is thick here and thins towards the south. If you measure the throw on the fault, you notice that actually, and you add in the sill thickness, you notice that the fault has actually lost quite a lot of displacement. And that's because if I just flick back, you'll notice that as this sill is inflated, not only has it formed a fold in here, but it's probably reverse reactivated the faults. Remember, these sills are younger than the faulted network, the fault network into which they were emplaced. You can see that because the sill is injected into the fault itself. And so we came up with a model for this like this. So we think, a sill was emplaced, it came up against this permeability contrast on its eastern margin. The sill started to inflate. We had a standard sort of ground deformation, if you will, as shown in here, but we actually inverted that previously inactive normal fault, removing some of its displacement. We carried on inflating the sill until some point we were able to inject an inclined limb on the western margin in here. We probably think there was some venting of material out in here, and then everything gets compacted. So this again was a bit of a headache when we worked on this with James Norcliffe, who used to be at Leeds, and trying to work out the relative contribution here of the faulting to the folding. And just to say, it's not just about sedimentary basins. We've done some work where we've looked at igneous emplacement into crystalline host rocks. So what some of you in the call today will be more used to working with in volcanic terrains. Craig did some work with us on the Alu Dome in the East African Rift, looking at the Alu Dome, or reinterpreting the Alu Dome as forming above a saucer-shaped sill, which was flanked by sill-derived vents, as you're seeing in the maps in here. So just to summarize and conclude, hopefully I've convinced you today that 3D seismic data is just like absolutely awesome and wicked. It images both the sills and the related ground deformation. So I think Tamara's wish was, for the airborne people, this has hopefully given you a bottom-up view of things. Folding and faulting both accommodate the ground deformation in different ways in different places, probably dependent on the host rock properties and the duration of sill intrusion. Stratigraphic analysis is really important for working out the sill age and also the kinematics, that trade-off between faulting and folding, and that post-emplacement differential compaction must be incorporated. Remember, because those sills are largely incompressible, but the sedimentary rocks are very compressible. And what we need is more borehole data, improved seismic imaging, so we can get a better handle on magma volumes. I've referred a couple of times in this talk to the fact that there probably is subseismic intrusions here, which may be modifying the relationship between the sills and the folds. And also allow us to have a better handle on the host rock and sill age composition and physical properties, because they're really important for things like depth conversion, understanding the deformation mechanisms. So thank you very much, and I'm happy to take questions if we have time.
Brilliant, thank you. Unfortunately, in this webinar, people can't clap for you, so I'll clap for everyone. That was brilliant. Thanks, Richard.
Thank you, Rich.
I'm going to let Chris read out and answer his own questions. I know Tim Wright's got a question in there, but I really wanted to get in with a basic question, and I'm the only one who can actually ask. I was wondering, are these very basic question? Are these environments in terms of tectonics only around active rift zones, or could they be anywhere in tectonic sense?
They could be absolutely anywhere, of course. So yeah, there's no. Our bias has been towards working on post-rift settings, and that's mainly because they are locations where there is lots and lots of high-quality seismic data collected by oil companies because they're exploring for oil and gas. So that's biased where we've looked. So Errigal is post-rift, northeast Atlantic margin, northwest shelf of Australia, Bight Basin, all of these places, New Zealand. That's biased where we've worked, but there's no reason we could not do this analysis in fold and thrust belts. There's no reason we couldn't do this in an area where there was just crystalline igneous rocks, of course, if there was an appropriate difference between the injected rocks and maybe the existing lavas, right? We just need that change of physical properties for us to image the bodies.
Right. Okay. That makes sense. Cool. Yeah. I'll let you get into Tim Wright's questions.
Yeah. So Tim's question, the first one is, do you have any constraints on the timescales of the intrusions? No, not really. So in the Errigal example, Tim, we use the seismic stratigraphy to kind of give this broad range of saying, well, it was somewhere between 12 and 15 million years of protracted emplacement. Now, your question might be more, do we know how long it takes to intrude one single body? And we don't know that. Because remember, what we're seeing in seismic data is one single seismic reflection, which could represent 100,000 years being uplifted. And then we're seeing stratigraphy, which is thinning across the top. And that stratigraphy could be thinning across the top of that fold over 5 million years. I guess my bias would be that some of these intrusions, well, no, let me back out of that. I used to have a bias where I used to think that the uplift would be like overnight, right? So you basically turn up one day and there'd be a 200-meter force fold in your back garden from a sill that was emplaced. And I guess now I probably am more of the mind that these are more protracted events. So they're probably happening over a longer period of time. Craig may be better positioned to talk about, and maybe some other people on the call, about where layered intrusions have been studied to the point where you could actually work out in the ages of individual magma batches, which then would get you to the time scales of the intrusion emplacement itself. And then Tim's other question is, can you back up densities at the time of emplacement? No, but we have some well data which would allow us to know the physical properties. And I was reading one, I think Juliet Biggs's papers the other day about basically contraction of cooling magmatic bodies. I think I was reading one of the papers that Juliet was a co-author on. And that was kind of interesting because it did make me start to think about, the differences in densities between sin emplacement, post-emplacement, and suprasil strain as well. So, can the cooling and the changes in the density and things like that, can they contribute to the ground deformation? But if so, the sills intrude at levels of neutral buoyancy. That we don't know. Probably because these are all relatively shallowly buried, and they are occurring at depths where there is a change in the stress state, right? So from basically sigma 3 is rotating, right, in these post-rift settings, so it's easier to lift the roof at shallower depth than it is probably deeper down where it's dike dominated, where it's easier to open horizontally. Rich has slightly replied and said the sills are probably placed at or above their neutral buoyancy when they're hot and molten. When they cool, they will densify. You spoke about decompaction of the sediments above, but what about below? Yeah, so again, Craig is probably on the call, but sorry, there's a small child screaming outside the door. We did have some ideas, I think in the Canterbury work with Jennifer Rees, as to whether the sills could sag into very wet and cold, shallow sediment, and whether that subsidence could actually lead to sagging across the top. Yeah, it could. But it's I can't say we have the answer, but it's a very good point.
I'll just point out there's 2 questions also in the Q&A box. Yeah.
Can net slip from the faults syntectonic to the sill emplacement help to measure the deformation induced during the emplacement? Yeah, so the we call it the scorpion sill, which was the example you're referring to. In the scorpion sill, the fault slip, I think, was about 80 meters of uplift. Before then, we think we have the fold related uplift. So yeah, in that case, we think there was 80 meters of uplift associated with that initial phase of magmatism. So I would say, yeah, there's an 80 meter uplift, and then that was increased to about, I think it was 277 meters. I think we had on that in the 268 meters. And then that was increased by, another couple of hundred meters during subsequent intrusion. Hopefully that answered your question. Xiaozi, hopefully I've pronounced your name right. You can give me a thumbs up if I have. Does 2D and 3D seismic data reveal sill complexes make a big difference? This is a really good point. So we started off working with 2D seismic data from the Dike Basin, where there is a spatial aliasing, of course, right? So you see these sills, but you'll have less certainty about the true map view geometry. You're still pretty confident. Well, you have less certainty around the map view geometry. With 2D data, you also struggle because sometimes you don't really know where through the sill you're going. If you're going through the thickest point, are you in a location where you're going through the thickest sill and the largest amplitude point of the fold? So there is an issue there. There are a couple of studies where, the Dike Basin study is a bit dodgy looking back. I wrote that paper in 2012, 2013, because there was some uncertainty about where those 2D profiles were with respect to the sills and the folds when we were doing the quantitative analysis. So yeah, I would always prefer to use 3D data if possible, but there is a large amount of work that can be done with 2D data still. Carlos has a question. Have you considered the crystallization / moving capacity ratio of igneous material versus deformation of the affected sedimentary rocks? No, sorry. No, I don't really follow the question. If you'd like to rephrase it, sorry, considered, you said. Have you considered? Yeah, sorry, I don't really follow the question. Sorry, but you can rephrase it if you want in the Q&A. So I just popped back to the chat, Tamara, because there was Tim says, thanks. My bias also suggests protracted, but only because we haven't seen a 200 meter sill appear overnight in the modern era. Yeah, that's a very good point. Craig is helping me out here saying imaging below sills is generally too poor to study compaction beneath them. Some field like Clayton show compaction primarily occurs above sills in Namibia rather than below. I think Clayton works on the Enken-Decker stuff, right? So I think he was looking at emplacement into non-marine red bed, sort of Aeolian sandstones and things which have relatively high depositional porosity. So if you were going to see a lot of compaction by weighting of dense intrusions into them, then maybe you'd see it there. Obviously, you'd see the same in water-wet marine mud rocks as well. But yeah. Eric's question is, sorry, I've got a kid here.
Oh, Daddy, when are you finish your call?
About 10 minutes. Okay. One day Corona will be over, right?
Yeah, imagine the day.
Imagine not being hustled out your own front room. Sorry, Eric says, is it possible to see any fabric changes on the outcrop scale of the emplacement before you match with the reflection data? Depends what you mean by fabric. If you mean fabrics within the emplaced intrusive body. I know Craig, again, was looking at some of these issues. Correct me if I'm wrong, Craig, there was a grant proposal you were putting together looking at layered intrusions, which would have shone some light on I think you were going to look at AMS analysis of fabrics and looking at composition and zoned intrusions, which would have basically been able to couple something to do with like the way the magma was flowing inside the sill as it was inflating. So going sideways in the sills, but also maybe the inflation as well, which is something which you could see in all of our models. We were thinking about whether you were emplacing a thin blade and then inflating, or whether you had a consistent thickness to diameter ratio through the intrusion event. So there's lots of interesting problems to deal with there. Hopefully, Eric, that partly answered your question. Somebody asking about, Sarah was asking me, did the cat make its escape? No, it's sitting on its perch at the moment across the room. And Paul Segal said, a comment saying, overlying layers are going to stretch and thus thin, even without porosity reduction. And so the question is, how well resolved are the steeply dipping parts of the intrusion relative to possibly disturbed zone in the faults? Yeah, that's a good point. So you can have, I guess, Paul, correct me if I'm wrong, but almost vertical flattening of the overlying layers. So as you're inflating the sill, because you've got a weight, depending on how deeply buried the sill is, of course, and in the Henry Mountains case, you could actually have almost boudinage and stretching of those layers. Your question then is, how well resolved are the steeply dipping parts? Quite well imaged. And the reason I say this is one of the reasons I wanted my speaker notes in the talk is I forgot to tell you what the dip of those inclined limbs are. So we often look at the seismic data vertically exaggerated, which makes them look quite steep. And they can be quite steep, of course. But if you depth convert the seismic data, what you often find is that the dips on those limbs are anything up to about 15 degrees. So they're relatively shallowly dipping, even though they cross-cut 500 meters of stratigraphy. They're transgressive limbs. So we actually think we have quite good imaging in most cases, because then at the end of those inclined bits, we see what we call outer sills. They go back to being subhorizontal, and then we have more confidence. The big elephant in the room is a different talk, of course, which is to do with seismic imaging of dykes and dike-related deformation. That's a whole bunch of other work. And your other question here is relative to the possibly disturbed zone in the faults. Yeah, I think I'm just trying to parse your question there. I mean, if you're referring to the last example I showed from the Exmouth Plateau, where we had the inclined limb injected into the fault, and again, I'm going to answer a question maybe you've not asked, but I'll try, and you can tell me if I'm answering the wrong question. But in the fault deformation zone, if you have enough damage, you can change the acoustic properties of the rocks in the fault zone, of course, and that can give you a discrete seismic reflection. And we see that in some seismic volumes. We see fault plane reflectivity. Here, if you go along strike of the sill, you don't see any fault plane reflectivity at all. It's only when you go to where the sill is in the hanging wall do you see that big reflectivity in the fault zone itself. So in this case, we think that we are imaging that, and we think the fault plane dip there is about 40 degrees. So it's still sufficiently shallowly dipping, or gently dipping, I should say, that we are able to image the igneous material that's been intruded into it. So hopefully that answers your question, Paul. Oh, right. I did. Wow. Okay, thank you.
I think that's all the questions that we have at the moment. Well done. And we're just on time for your promised 10 minutes.
No, there's no problem at all. Yeah, the kids, you'll make 3 big fans in our house if we hit.
If we hit proper time. Well, thank you so much. I think that was great. I certainly learned heaps. Thank you.
Yeah,
big claps again. And it was great to have you here. And for anyone watching, the YouTube video will go up online in a few days. Let your friends know, and keep an eye on your emails for the next COMET webinar information.
Yeah, thank you from me. And if there's anybody who wants to talk about any of this, because I'm new to COMET, of course, and I think we've talked to Tim and Andy Hooper and Janine and a few other people about trying to apply some of this understanding to things that have been studied in different ways. And, Tim's point about we've never seen this in the modern era then kind of calibrates what we think we're saying in the seismic domain. So please don't hesitate to contact Craig and I with critiques or questions, or if you want to have a chat with us and show some data that you've been working on, that'd be absolutely awesome. So thank you for the invitation.
Cool.
All right.
All right. Thanks, everybody.
Thank you. Bye.
See you later. Bye.